Thank you, George. Quite a few years ago, an engineer from Intel Corporation was visiting my campus in San Francisco and came by the computer room where I was working with one of my assembly language programming students. We were looking at a display I had created in an attempt to explain how interrupts work, and that an assembly language programmer has to always bear in mind that between any two assembly language instructions there could be an interruption, and sometimes those can have effects that would degrade the correct working of the assembly program. The Intel representative saw my screen and came over and said, "Where did you get that program?" And I said, "Well, I wrote it as a class demo for my assembly programming students." And I said, "By the way, while you're here, one thing it shows is that there's an unusually large number of so-called spurious interrupts occurring. These are false alarms, kind of like a leaky faucet. It takes away from the CPU's performance." And he kind of grinned and said, "Yeah, we know, we're working on it." And that experience convinced me that this kind of tool that lets you, in effect, have a way of seeing inside the computer what's going on can be valuable not only for diagnostics, but as well as for explaining how things are actually working if you're confused about it. So I plan to show you today a program similar to the one that I had shown to this Intel representative. He asked if he could take a copy of my program back to Intel to show his colleagues, show them what customers were now being able to see was happening. The organization of this talk is really in two parts. There's a high-level part where I'm going to advocate writing programs that do dynamic visualizations. But then I'll show you one particular case and invite you to use your imagination to construct other kinds of dynamic visualizations. The focus of this talk will be on using the Linux operating system, which is free, along with all of its development tools. And if you have your own computer, you can easily become supervisor and execute the special commands that we'll need to look inside the kernel. So my term dynamic visualization refers to a type of program that lets you see what's going on in real time. And there is a famous example of a program sort of like this that system administrators frequently reach for when performance is not what they expect. It's the top program, and it looks to see all of the tasks that are currently executing and how much CPU time each task is consuming, and sorts them with the most voracious user at the top and lesser users down. So you can see the percentage of CPU time being consumed by a particular task. And the screen will change periodically because the scheduler changes which tasks are currently being run. However, this can't be really considered to be a real-time display because the update is very slow, about once every 3 seconds according to my stopwatch. So my program is similar to this in what its aim is, but it differs in that it will give a continuously upgraded screen. Now, I need to just indicate what the overview is of how the system software interacts. An application program like TOP, or like the one that I will show you, runs in user space where there are severe restrictions on the privileges that the program can exercise to get at information in the kernel or get at hardware information. But the application program can make calls to runtime libraries using well-known documented interfaces, and those libraries know how to call the kernel to get at information about the kernel's data structures or about the hardware. And with Linux, we have the possibility of installing a piece of code that we have written, installing it in the kernel where there are no restrictions on what it can do. And so that's the concept behind this particular visualization. I should mention that if you're going to update the screen constantly and you're going to make use of the full screen, you need to change the way the terminal output normally behaves. Normally, the terminal is arranged so that characters get added at the bottom of the screen, and when they reach the end of the line, the whole screen scrolls up. And that is not going to produce a pleasing kind of display. So there are some ways we can change the behavior of the terminal output. I don't know if these are very old ways. They've been around 30 years, but I don't know if they're still taught in college courses. So let me just briefly indicate the idea here. The old-fashioned teletype, typewriter-like terminal is the model for the behavior of terminals by default. And there's a blinking cursor that shows where the next character will be added to the current display. We need to get rid of that cursor. We need to get rid of the echoing that occurs automatically when the user hits a key. And we need to have no scrolling. And we need to have no buffering. And so the way to get rid of all of those is to activate what's called non-canonical keyboard input-output. And here's how you can achieve that. First, there are special standard escape codes, they're called, that allow you to clear the screen or to home the cursor or to turn off the blinking cursor if it's going to be a distraction, and to position the cursor for the next character anywhere on the screen that you want to. And so these are the kinds of escape codes that are used, and there's a little language you learn pretty quickly to control that. How many people have studied these in courses or heard about them in programming? I'm guessing nobody has. Well, a couple of people have nowadays. They're the way a lot of programming used to be done, and they're very useful for these visualizations that I'll describe. To change the buffering and the keyboard echo behavior, here's the way that happens. There's a library function called terminal control get attributes that allows an application to get a copy of a data structure from the kernel that drives the behavior of the kernel, of the terminal output. That copy needs to be saved so you can restore it before your program ends. Otherwise, when you go back to the command shell, it won't behave the way that you would expect. So save a copy, but then make a copy to change some data, and install that back in the kernel, and that will get rid of the default behavior. Now, the visualization application I'm going to show you has two pieces of code. It has an application program written in C, C++ really, and it's required to have an entry point named main, as you probably know. In addition, there's another piece of code that will be installed in the Linux kernel, and it does not have a main, and it has to be written in C, not C++, in order to interface with the rest of the kernel code. And it has to have two entry points named init module and cleanup module, rather than having a main program. When the kernel module gets installed, this function, which you can define, will automatically be executed. And when you're done and you want to remove your module from the kernel, perhaps to make some changes and install it again later, when you remove the module, the cleanup function that you write will be executed. If this is all there was, there wouldn't be any point to having the kernel modules, but these are mandatory functions, and then you will add your own particular payload functions to this, depending on what your objective is for this module. So that's a little bit of overview about writing dynamic visualizations. Now let's focus on a specific instance of this where we try to visualize interrupts. What is an interrupt? Well, this slide tries to briefly explain that. I'm going to make these slides available, but the idea is that whenever there is some change of state in one of the peripheral devices attached to your computer, a change perhaps that the system needs to keep track of, like a user pressing a key or the user moving the mouse, that could happen at any time, and it needs to interrupt whatever program is currently running briefly so that the kernel can note the change, record it, and then resume executing the program. That's the concept of an interrupt. Now here's an overview of the hardware components inside a modern PC such as this laptop. My laptop computer has a Core-2 dual processor, which means there are two logical CPUs, and they're running in parallel. There's a component known as the memory controller hub, which is designed to read and write from memory, transferring the data into one or the other of those CPUs as needed, and also for fast control of the graphics display. But there's another component known as the I/O controller hub, which is our main focus today, which has all of the various peripheral devices attached to it, and which in a modern system communicates information back and forth from those peripherals using little messages, very much like Ethernet packets. They're not Ethernet packets, but the same principles apply. They're short messages containing data that go back and forth on a PCI Express bus. So whenever the printer runs out of paper or toner, or whenever the mouse is moved, or whenever a disk drive finishes writing a sector to the hard disk, that needs to be noted by the CPU that's keeping track of everything in memory, and so an interrupt will be generated. They come from these peripheral devices. This slide simply goes through a list of examples of state changes such as I have mentioned. The important thing here is that each different kind of device needs to be responded to in a different way. And therefore, there have to be a number of so-called interrupt handlers or interrupt service routines specifically designed to handle each type of interrupt coming in from the different devices. There are quite a lot of these interrupt handlers, and one of the big jobs in writing an operating system is to create these handlers for all of the different installed devices or potentially installed devices. In the Intel architecture, there is a data structure that the operating system builds in memory consisting of addresses for these interrupt handlers. It's called the interrupt descriptor table. It has room for as many as 256 different possible interrupt handlers. And the CPU always knows where it is in memory by referring to a special dedicated register inside the CPU called the Interrupt Descriptor Table Register, IDTR. There are, of course, other registers in the CPU. Some of them are involved in handling interrupts. And elsewhere in memory is stored the code for each one of the different interrupt service routines. There would be 256 of these routines altogether. Here is the, if you haven't looked at Intel's documentation, here is the layout of the information in one of these interrupt descriptors. And there, as I say, there are 256 of these. The important information for us is stored in two different places in one of these descriptors. It's the address of the entry point to an interrupt service routine. And on typical systems now, these are 32 bits. They sometimes may even be 64 bits, in which case the structure has to be bigger. But the least significant word is stored in one place in this descriptor, and the most significant word is stored elsewhere. And as we'll see in some of our code, we have to extract these two pieces and put them together if we're going to realize this interrupt visualization. Now, the typical personal computer really does not have 200 or more different devices attached to it. It only has a small number, or maybe a dozen or 2 dozen. So do we really need all these 256 different interrupt handlers? That's one question, and the visualization will shed some light on that question. Another question is, when you read the textbooks that explain the idea of interrupts, you're left to wonder, well, how often do they happen? Do they happen only occasionally, maybe one an hour, or one a minute? Or are they happening very, very frequently? Are some frequent and others seldom? That's the kind of thing we'll be able to understand once we see the dynamic visualization. Now here is a static screenshot of the kind of display I'll show you, and this is what I showed to the Intel engineer. It's a display of the 256 counters that are incremented each time a particular one of those interrupts occurs. And most of them in this display are still at 0. The interrupt has never occurred. And so to keep from displaying a clutter of zeros, I've shown those as dashes, so it's easy to just visually screen those out. But there are a few where we can see there's been a substantial number of occurrences of interrupts at the time this screenshot was taken. When we see the live display, we'll see these counters turning over as interrupts occur. If I want to encourage any of you to think about writing your own visualizations, then perhaps I should allay any concern you may have that we're talking about writing a massive program. No, these two pieces of code, the kernel module code and the application code, they're really quite short. And if I left out all the comments, they would fit on less than 5 pages of printout. So it's not a large number of instructions to create this visualization. Here is the multiprocessor version of the visualization. There's not enough room on the normal screen to show counters to as many significant digits, but we will be able to see some things happening, namely different CPUs are handling different interrupts, and occasionally there's a CPU that is there's a case where both CPUs handle the same interrupt. And so when the time comes for the display, this is what the screen will look like for the multiprocessor visualization. What makes the multiprocessor version possible is the fact that inside each CPU there's a set of registers that comprise what is called by Intel the local advanced programmable interrupt controller. And one of those registers holds the ID number for the CPU. So in one of the CPUs, that register would hold the value 0 and the value 1, and if there are more logical CPUs, they would have different ID. And the CPU can get directly to its own ID number, although it cannot see the ID number of any other CPU. So when an interrupt occurs and it's dispatched to a particular CPU, that CPU can find out what's my ID number and can append that ID number to the interrupt number in order to know which counter to increment, so that I can have 512 counters. The first group, the first half, are processed by CPU number 0, and the rest are processed by CPU number 1. I should also mention that there is another piece to the advanced programmable interrupt controller called the InputOutput API C, and that component is part of the I/O controller hub, and that's the programmable piece of hardware that controls how the signals, the interrupt signals from the various devices, how they're going to get routed to specific interrupt numbers among the 256. When I showed Professor Ledin my demo several weeks ago, one of the questions that he and Roger asked me was, well, how do you know which of the counters goes with which device? And there is some logic to this, although I have to warn you that the Linux developers keep changing their minds about how they want to dispatch these device interrupts to particular ID numbers, particular interrupt ID numbers. So if you look at this week's kernel, it may be different from what they decide to do next week or next month. But they seem to have a habit of always documenting what they're doing in a particular file, which I've indicated here. It's called the IRQ, Interrupt Request Vectors file. It's one of the header files that's part of the kernel. So if you're confused by changes that you notice, you can go to that file to help yourself straighten them out. In the current Linux kernel that I have installed, this seems to be their plan. They have no choice about what to do with the first 32 interrupts. Those are reserved by Intel. And they're not really handling, for the most part, they're not handling device interrupts. They're handling situations where the CPU interrupts itself because of some fault, some privilege violation that it has detected, or an attempt to divide by zero, some kind of error condition that will trigger one of those interrupt numbers in the top row. And then, on a symmetric multiprocessing version of Linux, they seem not to use any of the numbers in the next row. Those are used on single processor versions of Linux, but not on the SMP versions. The SMP versions can use the rest, and it's up to the developers to decide how they'll be used. And you'll see that for the most part, they don't use very many of them, and the ones they do use tend to be from column number 1 or column number 9, with a few exceptions. And then at the bottom, there are interrupts that are triggered when one CPU sends a message to the other CPU, called interprocessor interrupts. And those are handled at the bottom, along with thermal interrupts. The temperature gets too hot, that can interrupt the CPU, or other kinds of error conditions. Those are handled at the bottom. There's also the ability of each CPU to keep track of time and generate a frequent timer interrupt, and this is the location for the timer interrupt. That'll be the one turning over the most rapidly when we see the demo. Let me wind up by making a few comments about writing Linux kernel module code. First of all, there is a little bit to learn. It's not like normal C programming. It's a lot like normal C programming, but not entirely. And the first 2 chapters of this marvelous book explain really all you need to know to get started writing your own kernel modules. There may be other sources as well for how you would teach yourself to do this. You'll quickly discover that there are some marvelous helper functions you can call if you're writing kernel code to do things like allocate kernel memory, or create a pseudo file, or install some inline assembly language, if that's needed, into your C code. Here is the organization I used for my particular kernel module. It has to have these mandatory administration functions that I mentioned a while ago. In addition, its payload consists of some data structures, including a couple of pointers to memory that gets allocated elsewhere, to some arrays, in particular an array of counters for the 256 different interrupts. And since it's going to create a pseudo file, that is an object in the kernel that looks to an application as though it's a disk file, but it's really not. Instead, its data gets created on the fly each time the application tries to read from the file. It's called a pseudo file. These are the functions I created to do the standard file operations on that pseudo file. The main one is we allow applications to read from the file, and what they're reading are the current values of the counters, so that those counters can be updated on the application screen. Now, the way that I managed to immediately update a counter when its particular interrupt occurs is by making a modification to the interrupt descriptor table. In the olden days, this was called hooking an interrupt. I'm going to create my own interrupt handlers, very short. I'm going to do 256 of them. And all they do is increment a counter and then pass control over to the usual interrupt handler. So that's called hooking an interrupt. This is not a new idea. It was advocated long ago in MS-DOS programs and used for famous programs like the clock program that keeps a running display of the time of day on the screen for you, or keyboard macro programs. So this is an old idea. I've just taken it to an extreme by hooking all the vectors. Here's the idea of how the hooking works. When we boot up Linux, Linux creates an interrupt descriptor table with pointers to all its 256 interrupt service routines, interrupt handlers. Here's one of them. What we do is allocate some memory and build our own table of pointers to our own interrupt subroutines. And then, when everything's ready, we disconnect the pointer to the original interrupt descriptor table and connect it to our new table. Immediately, as interrupts occur, our routine will execute, and what our routine will do is two things. It will update an appropriate counter, and then it will extract the address of the original interrupt handler and put it on the stack so that it can jump over there with a return statement. So if you're curious about how this would actually work, that's the picture of what's going on, multiplied by 256. Now, we don't want to write 256 interrupt service routines. It takes too long to type them in. So we can use a facility that's provided by the GNU assembler called a repeat macro. And here's how that would work. There's a small block of code that I want to be created for each one of my 256 routines. So these two instructions get replicated with a different interrupt number for each of the 256 cases. And then this routine jumps to a common entry point where we make use of the number that got pushed onto the stack that identifies which interrupt number, which counter should get incremented. Registers need to be saved if we're going to be using them. So here we get that interrupt number, we increment the appropriate counter, and then we copy the original handler's address to the stack so that we can restore the registers and get out of here with a return back to the original interrupt handler. I understand that many of you who take the assembly language course here now are doing 64-bit assembly language. This is 32-bit assembly language. So if you wanted to imitate this idea, you would need to go in and make changes to the registers. Instead of EBP or ESP, it would be RSP or RBP. The process of compiling one of these kernel modules that's written in C has been made complicated in the most recent versions of the kernel. It's not enough to just invoke the C compiler. You have to compile your module against all of the source code for the current kernel running on your system. And it's a little bit complicated to set that up, and so in the classes I teach, I don't want my students to get bogged down with that, so I've written a little program, a utility program, that will do all that in one step, so the students don't have to even think about it. My program is called make, M for module, and you invoke it the same way you would the normal make program. Just tell it which module you want to compile. Then, when it's time to install your compiled object file called a kernel object, a special command has to be used that's usually reserved for the supervisor user, for the root user. And so you would need special privileges at this point in order to execute this command that installs a module into a running kernel. In a college course where we allow students to do this as part of the curriculum, we have changed the permissions on this command file so that students do not have to be root user. They don't have to they can execute this with no problem. But at many schools, especially schools where they teach students how to write viruses, they might not want to allow students full privileges. And once you can install modules, in effect, you have full control over the machine. So I don't know if Sonoma State would want to adjust the permissions on the install module or not. But if you have your own computer, you can do this with no problem. So here are a few ideas of mine for some exercises you could try, so homework that I might give to my students, just to get you started on writing dynamic visualizations. Could you modify the code that I'm going to make available so that it runs on a 64-bit kernel instead of a 32-bit kernel? Or could you modify it so that it could work with 4 processors, a Core-2 quad CPU instead of a Core-2 dual CPU? Or could you think of other kinds of visualizations that you might learn a lot from seeing? If you get interested in this, I'll mention these resources that are on the internet, on my website, and on the official Linux kernel website. The current version of the kernel can easily be downloaded from kernel.org, and all of the code that I'll show you in a moment can be downloaded from my website at this address at USF. Now that's the end of the slides. Let's look at the demos. The first step is to install the kernel module. The source code file was named activity.c, and the compiled version is activity.ko for kernel object. So here's the installation of that. If there's any problem, you'll get a warning message. If you get no warnings, everything worked fine. I even have my module print a message to the log file, which we can see confirming at the bottom here that it did get installed. Next step is to run the application. Its source file was named activity.cpp. It's a C++ program, although really it's a C program with the ability to use C++ commenting and the ability to delay declaring variables until the point where you actually need them. At any rate, it's been compiled to a binary executable named activity. And so here's the display. As each device is interrupting, we see its corresponding counter get incremented. One of the things to notice is that these interrupts are greatly over-provisioned. We really do not need 256 of them. Most of them are not doing anything. Of course, in a few cases, they're not doing anything because we haven't changed the state. I could move the mouse and we'll see a different counter getting incremented. It's the one near the bottom in row E, column 9. Or if I move my finger across the mouse pad, you'll see another interrupt occurring up there in row 3, column 1. Oh, sorry, column, maybe that's the, where is it? Yeah, 89 hex. You can see the local API C's counter turning over very rapidly, and some other interprocessor interrupt activities are happening in the bottom. I guess haven't taken time to nail down exactly which one does what. If you're connected to a network, as packets arrive, you'll see interrupts occurring to handle those receptions. If you unplug the USB mouse or plug it into a different USB port, you'll see a different counter get activated. And I've also written a few application programs that will trigger specific interrupts just so you can verify that things are working as they should. For instance, I wrote a little program called ZeroDiv to do an attempt to divide by 0. Oh, sorry, I'm not in the right directory. Now, when that happens, the processor will automatically generate a particular interrupt number 0, in fact, which will kill the program and allow Linux to print a message telling you about that fact. So here's what happens. Interrupt number 0 got triggered, and the Linux service routine prints a message that says floating point exception. That's actually incorrect. It wasn't a floating point exception, but that's the message that Linux prints. Another case is a little program that tries to execute a seldom used instruction called bound. Its purpose was to check for array bound accesses beyond the bounds of an array. One of the common ways that viruses gain control of a computer is by overflowing the bounds of an array. And so the idea of this instruction was to trap any attempt by a program to access beyond array bounds. So I've set it up so it will try to do such an access, and that will cause the CPU to generate interrupt number 5, the bounds error overflow exception. So I called it overrun. So watch number 5 and you'll see it get executed each time you run this program. I'll mention that up at the top, you guys don't have a pointer, do you? I can't reach that high. But up at the top, the one that's spinning very fast under the letter E, that's the page fault exception interrupt. And as processes are being scheduled and their memory, their attempt to access memory occurs, if the memory's not been mapped, that'll cause a page fault. And every time that happens, we see it being counted, and so you can see there's quite a lot of page faults occurring in the background here. Under number 7, that is the floating point exception handler. Every time a program tries to use any of the floating point instructions, those registers do not automatically get saved every time a task switch occurs. Not many tasks really need those registers, so a lazy context switch philosophy is employed. Only when an instruction attempts to use one of those registers will the operating system say, you've switched tasks, you didn't yet save the registers, you better do that now before you clobber somebody else's work in the register. So this is how often that is happening, the lazy context switching on the floating point registers. So that's the idea. And if you have never seen a display of this kind, it may be quite insightful to realize, okay, you don't have 256 of them going off all the time. There's only a few. Some of them are happening very often. Some of them are not happening very often at all. There's plenty of unused slots in the interrupt descriptor table if you wanted to add enhancements to your code. I think it's a useful kind of insight to have, and it's pretty quick to see it. I'll mention that the spurious interrupt phenomenon that I mentioned a while ago, if it were to occur, it would be counted over here in this last interrupt, the way that Linux has programmed things. And what we see is we're not getting those spurious interrupts caused by electricity leaks. They're not happening. So Intel has fixed that problem. Now I have the dual processor version, which is advertised in this talk. I'll show you that. First, let me remove this module. and install the SMP version. So here, if we move the mouse, we see that all of the mouse interrupts are being handled on one of the CPUs. I'm not sure I see which one. It should be the same as a while ago. Let's plonk this back over. Looks like E9 gets changed on CPU number 1 when I move the mouse. For the mouse pad, that's being handled by the other CPU, 89. So the Linux programmers have programmed the I/O advanced programmable interrupt controller to do the routing, and they tend to send half of the interrupts to one CPU and half of the other. That's kind of a fairness philosophy. Some of the versions of the kernel even implement an optional policy called IRQ balancing, where for a little while they'll send all the mouse interrupts to this CPU, and after they've sent 10,000 or so to this CPU, then they'll reprogram the I/O API C to send them to the other CPU to balance out the time taken away from tasks to handle mouse interrupts or other device interrupts. Let me pause and see if there are any questions, and then I have one more short demo.
Any questions?
Yeah.
So running something like that does cause interrupts on the computer itself. Can you see that actual program's interrupt in there, or do you know where it is?
The
Program itself, does that cause interrupts?
Great question. Linux has changed its philosophy in recent times about how it does system calls, which is, I believe, what you're asking about, when an application needs service from the kernel and will need to interrupt the kernel. For many years, Linux did this by executing a software interrupt instruction, interrupt 80 hexadecimal. And so we would see that happening here if it happens. But recently, especially on the SMP versions of the kernel, there is a new, faster way to get service from the kernel that doesn't involve changing so many registers and switching stacks. It's a fast system call capability, and that will not show up here. It's not an interrupt. It's a call, but not an interrupt transfer. So that's why with the SMP version we won't see interrupt 80 turning over very often. Now, the SMP version of Linux also is able to run legacy applications which still have the interrupt 80 instruction, and so we will see occasionally some of those older programs make calls in that way. How many? Yeah.
What would cause interprocessor interrupts?
The kernel needs to maintain a mapping of physical memory to virtual memory addresses. And each processor has its own maps, although they share some of the maps. If some program does something that causes a need for one of those maps to be changed, the other processor also needs to know about it. And so in that situation, the CPU will send what's called an interprocessor interrupt to the other CPU, interrupting it so it can make the corresponding changes to its tables. And there are other situations where that would also be a need. Yeah.
That first program that you showed that just had one CPU, was that the sum of the interrupts of
Yeah.
the two cores?
Yeah. Now, when I started preparing for this talk a few weeks ago, I was also working on a new project I was telling one of the faculty here about it, I wanted to try and understand the universal serial bus. There are books about this that I've tried to read and I cannot understand them. They're too high level. I'm not able to see really what's going on down at the hardware level. So it occurred to me, well, why don't I create some kind of visualization that will help me get a concrete hold on what's going on? And so I haven't finished that process, but I have begun it. And it's really helps a lot. And here's my results so far. I created a little module called USB hubs. I'll install it in the kernel so it can get to the hardware. What's wrong? There it is. Oh, I didn't type the command correctly. No problem. Now, what that module does is to create a pseudo file which I can access by using the cat command to draw the contents of the file onto the screen. And it's like most pseudo files, it's in the proc subdirectory and it's named USB hubs. So there it is. And what it should be doing, why is it not doing what I want it to do? It's not turning over. Oh, I know why. Because this is only reading the file once. So I have a separate program that reads and rereads and overlays the previous display with the new display. It's called Dyna for dynamic view. What did I do wrong? Oh, dynamic view applied to this proc file. There. So there are several USB host controllers in my laptop PC, 5 of them in fact. Some of them are idle because nothing's plugged into the port, but a couple of them you can see are fetching and executing what are called schedules. They're instructions for the USB processor. And you can tell which one goes with which device by unplugging the radio device to my mouse, and you'll see that one of those hubs stops fetching and executing instructions. Or we can plug it back in and it will restart. Now, what you see at the top are the names of the various registers in the hub controller. And the particular one is the frame base address, and that's pointing to a location in physical memory where all of the instructions are stored for the USB hub processor. And so with a tool to go in and look at memory, you can go and study those little instructions in detail and begin to see, oh, that's what they're talking about in the books about USB. So I find that these visualizations are extremely helpful in clarifying what I hear about and what I read about.
Thank you. Unfortunately, we have to repeat the room.